Okay. Um, so as we sort of go into the last three lectures of this class, I want to wrap up the sort of auction mechanism design part of the class and jump briefly into thinking about information, and in particular, like increasingly connections between the kind of stuff we've been studying, algorithmic game theory, and machine learning. And the machine learning aspect of it will become increasingly apparent over this sequence of three lectures. In this first lecture, I'll just sort of mention connections at the end, but we'll be sort of jumping, straightforwardly into information. So, okay, we've spent a lot of time thinking about auctions, which are very much about like the physical world. We're like allocating things, and we're collecting money. And our focus has been on the things that we allocate. We want to maximize welfare, or on the money we collect. Like we want to get rich. And yeah, and so those have been sort of the focus. What I want to ask in this lecture is how we can apply the same kinds of ideas. We're still going to want to design mechanisms that are going to elicit somehow truthful reporting of beliefs. But unlike in auction design, those, the truthful elicitation of beliefs, it's not a means to an end. It's not that we want to truthfully elicit beliefs so that we can allocate goods. It's the beliefs themselves that we want to elicit. And we'll be thinking about sort of correspondingly more complicated settings, like not single parameter domains, where people might have complicated beliefs, and getting them to tell us what those beliefs are. That's sort of the whole purpose of our investigation. Okay. And so the problem I want to think about in this class is, how should we contract with an expert? So like, someone who might have substantially more informed beliefs about what's going to happen in the future, like, who's going to win a presidential election, or, which of two competing video distribution formats is going to become dominant. Something that we will eventually observe the outcome of, but we want to like elicit informed beliefs before the outcome is observed, from someone who has better beliefs than us, right? If we were experts in everything, we wouldn't need to elicit beliefs from other people. But like we're experts in algorithmic game theory, not necessarily in politics, and so we might not be the people best positioned to estimate the likelihood, say, that Biden wins the next election. Okay, so let's just sort of like to fix ideas. Let's think about like a special case of like betting on an election outcome. So suppose we want to know the likelihood that candidate A wins the next presidential election, which we know to be between candidate A and B. Okay, and just to sort of, this will be a bit informal. We'll fix a model in a little bit. But like to give you the vague, outlines of like the setting, eventually I'm going to learn who wins the election. Right? Eventually I will learn like A wins the election or B wins the election. At that point, I can pay the person whose beliefs I'm trying to elicit today. So like the general idea is I want to write a contract such that some person that I believe to have informed beliefs will tell me their beliefs today. Then I will observe the outcome that actually occurs later. I'll see who won the election, at which point the contract will specify some amount of money that I should pay them as a function both of their reported beliefs and of the outcome that actually occurred. And I'd like to write the contract so that if the person whose beliefs I'm eliciting today wants to maximize their expected payment in expectation under their own beliefs, then the best thing they can do is to tell me their beliefs correct. That's going to be the setting in broad strokes. Okay, and in general, there could be lots of different outcomes. But what I want to walk through sort of a little toy example where the outcome space is binary, doesn't necessarily have to be. But the relevant thing is that I don't know the outcome now. I want someone to tell me their prediction for what's going to happen now, like a probabilistic prediction. Like I think there's a 30% chance that A wins the election. Eventually, I will observe the outcome, not a probability, but like like A won the election, at which point the payments are made. Okay. Okay, so we want to know the likelihood that some candidate A wins the next presidential election between A and B. We could just introspect. We could like think to ourselves, I think there's like a 20% chance that A wins the election. But, like that wouldn't be very valuable. Like we do not have especially informed beliefs. We are algorithmic game theorists. We don't follow politics. And so as it happens, we have a friend who's a professional gambler who is also a politics wonk. So like this guy has informed beliefs. Like he's, watching the nightly news, he's following everything. Of course, nobody can tell the future, but like we think that this guy's beliefs are probably better than ours, and we would like him to tell us what they are. Okay, but he's this compulsive gambler. And so like despite the fact that he's our friend, if I just like ask him what his beliefs are going to be, he's not going to tell us, or he's not going to, tell us sort of the sharpest version of them. In fact, maybe it takes him a little bit of effort to after we ask him the question, to really come up with his best estimates. And so he's basically only willing to do it in exchange for money in what will eventually, what will amount to a gamble, right? Like what he says is, okay, like what's in it for me? You offer me a contract that's going to pay me as a function of what I tell you and what actually happens. And then I'll do it. I'll play your game. I'll report to you I'll give you the report that I think, under my real beliefs, will maximize my expected payout. Okay, and the name of the game here is what that contract should look like. Okay, so how can we set up a gamble so that if this guy wants to maximize his payoff, in that case, he will tell us his true beliefs? Okay, by the way, like his true beliefs, there need not be some like connection between his true beliefs and like the truth. It's not even clear whether, it is a coherent concept, the probability that A wins the election. Like what is the probability space that is taken over? It's not clear that's a coherent concept. So we don't need we don't need somehow for this guy to know the truth. We just want him to tell us his beliefs. And the presumption here is that when he's computing his expected payoff, he will compute that expectation under his beliefs. That's going to be what's going to allow us to contract to incentivize truthful reporting. Okay, so let's think about this. Let's start with maybe some like straw man attempts. Like what could we possibly do? We could start with like the easiest question. Like we could say, who do you think is going to win the election? And of course, he's not going to just give us an answer. We have to make it a bet. And so you can make it a bet. You'll say, okay, who do you think is going to win the election? I will give you $1 after election night if the person you told me today was correct. Okay, so let's just betting on the winner. Okay, so what is our friend going to do in the face of this bet? Yeah. Yeah, he's going to tell us who he thinks is more likely to win the election, right? Like what should he say to maximize his profits? Well, like if under his beliefs, he thinks that A is more likely than not to win the election, then if he tells us A, then he believes that he has at least a 50% chance of getting $1. And if he tells us B, he believes he has at most a 50% chance of winning $1. And so the thing that will maximize his payments under his own beliefs will be to tell us A. Similarly, if he thinks B is more likely than not to win the election, he'll tell us B, right? Okay. And so this sort of, this kind of bet does get him to correctly tell us who he believes is more likely to win the election, but it didn't elicit all of the information that we wanted. We wanted to know like what he thought the probability was that A would win the election. And this kind of bet does not distinguish between the expert thinking that A has a 51% chance of winning the election and the expert thinking that A has a 99% chance of winning the election. Either way, his best response here would be to bet on A. Okay, and so this is a fine bet as far as it goes, but it's eliciting something very coarse. It's just eliciting from him whether he thinks A is more likely to win or B is more likely to win, a single bit. What we would like to do is elicit more, the probability that he thinks A wins the election. We'd like to be able to like write down a bet, a contract that in the first case will cause him to tell us, I think there's a 51% chance that A wins the election. And in the second case, will cause him to tell us, I think there's a 99% chance that A wins the election. Okay, so is the problem clear? Like the thing that we're trying to do? Like this guy has beliefs. In this simple case where it's just, a binary outcome, those beliefs can sort of be boiled down to a number. What is the probability you think outcome A is going to occur? I'd like to write a contract that is allowed to depend on the outcome, like is allowed to depend on the winner of the election. So I will eventually observe, does A win or does B win? Of course, I will not eventually observe anything of the form A had a 59% chance of winning. Like, that's not even necessarily a coherent probabilistic notion. So I only observe the binary outcome, but I want to write a contract that will allow me to elicit from this expert, like, the real valued belief. Okay, the general problem makes sense. Yeah. Let's assume you can model this in different ways, but yeah, in this lecture we're just going to model our friend the gambling politics wonk as a pure expectation maximizer. Doesn't care about variance. Yeah.
100,000 friends, like asking.
Well, if they all have the same belief, they'll all predict A in this case. Like suppose I in fact have 100,000 friends, but they're all clones of each other. They all have the same belief, right? They'll all take this bet. If they think there's a 51% chance that A wins, it's not that 49% of them are going to say B. That would be a dumb thing to say. If you think there's a 51% chance that A wins, they would all say A. And so merely cloning my friends is not enough to solve this problem as easy as that would be. Does that make sense? Yeah.
Like big 100,000 bets of different lines with high probabilities going from like point basically epsilon to epsilon chance that like A wins to like epsilon chance that B wins. Offer them all to your friend, just like see where the which one's in the
Like offer a menu of choices and let him take only one of them.
At most one of each, and just see where the boundary is between the ones he's taking and what's not taking.
You could imagine trying to do something like that. You'd have to think about, the discretization and whether there are like arbitrage opportunities and how much money this would cost you to offer all of these bets. But you could imagine going down that road. Yeah, I mean, like this is obviously not the solution, and we're going to need a different solution.
Oh, I just like make a market on the probability, and then like if it's above his belief, it's his expectation to sell it.
produce some kind of like prediction market.
Yeah, where like rather than like paying him, just if he's right, it's like he has to like stake something. So if he thinks like EV is like 70 cents, for example, if you charge him more than 70 cents, then he'll want to sell it. Otherwise,
Yeah. Yeah, you could imagine all sorts of things of different complexity. There are prediction markets. You'd have to think about how to design them. The place I'm going to go is we're going to look for sort of a simple solution, but a solution that happens to be, not that we're not going to talk about it, but happens to be sort of a core object in the design of prediction markets. Okay. So like one thing you might notice here, it's not just that our contract like wasn't good. It's like we didn't even ask the right question. Like I didn't ask him what was the probability that A would win the election. I said, who do you think is going to win the election? So like just as like a, sanity check, like what if we just ask the right question? What if I say, okay, look, what do you think is the probability that P will win the election? That's the question I intend to ask. That's the question I want the answer to. Of course, now I need to think about how to pay him, right? Basically, I need a payment rule that says as a function of P and the event, whether A won the election or not, how much money do you get? Okay. And so you could think about like how we should do this, and like probably you wanna, if A wins, probably he should get more money the more confident he was in that, right? Like if he said there's a 51% chance that A wins and A wins, probably we should pay him less than if he said there was like a 99% chance that A wins and A wins. Like to the extent that he has more confident knowledge, we want to give him some explicit incentive to tell it to us. Okay, probably like if he thinks it's really likely that A wins, he should get more money if A wins compared to if B wins, right? Like simple things like this. And so maybe here's like the simplest version, right? Like I could say, look, you told me there was a P% chance that A would win. I will pay you P dollars if A wins. That's the probability you told me you thought A would win. And if B wins, I'll pay you 1 minus P dollars. 1 minus P is the probability that you thought B would win, because here there's only 2 outcomes, right? So I'll just say, look, whatever event actually occurs, I will pay you in proportion to the likelihood that you ascribe to that event. Okay, so you get more money for events that you specified were more likely to occur, and the more confident you were in those events, the more money you get. Seems like a, not a crazy payment rule, right? Maybe the first thing you'd think of. What's our politics wonk gambler friend going to do in response to this contract?
Even if you think A winning has like 51% chance to report 1.
Yeah, like we asked the same, we asked the right question here, but we elicited the same behavior as the last contract, right? So what's he going to say to maximize his profits? Well, we can sort of go through his thought process, right? Like, suppose that our friend believes that A will win with some probability Q. That is his belief, okay? And now he's thinking what probability P he should report. What we would like him to do is report P equals Q. But what's he going to do? He's going to like think about, under his own beliefs, what is the expected amount of money he's going to make for every report he could present, right? So let's call that SPQ. This is going to be the expected amount of money he makes in expectation over his own beliefs, which is that A wins with probability Q if he reports P. Okay, well, how much money is he going to make? Well, if A wins, which he believes happens with probability Q, he makes P dollars. And if B wins, which he believes happens with probability 1 minus Q, he makes 1 minus P dollars. Okay, so for him, Q is a constant. That's his belief. P is a variable that he's optimizing over. Okay, now this is like a linear function, right? Like, Q is a constant. So he's going to get some convex combination of P and 1 minus P. Or sorry, he's like, he's going to get some convex combination of Q and 1 minus Q, where the weights of that convex combination are specified by his report, right? So he will never have incentive to report something indecisive, like 75% chance that A wins, right? Like maximizing over some convex combination, like it's always going to be maximized at one of the extreme points. If he believes that Q is bigger than 1 minus Q, right? The probability that A wins is bigger than the probability that B wins, then he can get in expectation Q dollars by putting 100% of his weight on the report that A will win. On the other hand, if he believes that B is more likely to win, that 1 minus Q is bigger than Q, he can get the most weight by putting 100% of his reporting weight on the event that B wins. Okay, so like if we offer him this contract, even though we've asked him the right question, like the only information he's giving us is going to be who he thinks is more likely to win, not the probability he thinks they're going to win. What he's going to do is he's going to ask himself, is the probability that A wins more than 50%? Is it more likely than not that A wins? If so, he will report 100% likelihood that A wins. Otherwise, he will report a 0% likelihood that A wins, 100% that B wins. Not that these are sensible probabilities, but those are what maximize his expected payoff under his own beliefs. Okay, does that make sense? So like even when we ask the right question, like figuring out how to write the contract is a little bit tricky. Like this wasn't a crazy way to write the contract. I think it was pretty sensible, probably the first thing many of us would have thought of, but it doesn't elicit the information we wanted from him. Does this make sense? Yeah.
So, like multiple contracts, which kind of about whether it's
You could, yeah. I think that was similar to a previous suggestion, sort of multiple bets at different odds. So you could try to do that. We're going to aim to do something simpler and just have like a single contract. But you know, like you could try to do that, and it would be a little messier. There'd be sort of discretization issues, and you'd have to worry about what you allow about, like are you going to allow them to take multiple of these contracts, and how do they interact? Good. Okay, but is the problem clear, and why it's not like immediate the solution? Okay. So let's now write down a model. Okay, so we've got some future event Y, for example, who's going to win the election. Okay, so Y is at the moment at which we're writing the contract like a random variable. Like we don't know. We will eventually observe the outcome of Y, but we don't know it at the time that we're writing the contract. And in our example, Y took values in just some binary space, like A could win the election or B, but more generally, that's not necessary. Like Y could take many different values. Okay, so you could be betting on some richer outcome space. So that's allowed in our model. Okay, and we're going to assume that the agent has some beliefs over how the outcome is distributed. Okay, so the agent's beliefs will be represented as a probability distribution over these finitely many outcomes. Okay, so there, again, these don't have to correspond in any way to reality. These are just the beliefs of the agent. What is relevant about these beliefs technically is that when the agent computes expectations about what their expected payoff is going to be, they're going to compute those expectations under their own beliefs. Okay, now we're going to offer some contract, some payment rule, which will pay the agent as a function of their reported beliefs and the outcome. Now, just as has been the case throughout our sort of mechanism design portion, the agent is under no obligation to tell the truth. The agent will report some distribution corresponding to beliefs. So let's call it P, also a distribution of our outcomes, but not necessarily Q. We'd like them to report P equals Q, but they could report something else if doing so is advantageous to them. And after they give us their report at some time later, we observe the actual realized outcome. Like we see who wins the presidential election, for example. Okay? The outcome could be arbitrary. It doesn't have to be drawn according to the agent's beliefs, for example. But at that point, we have this contract that will specify what the agent is paid. Okay, the agent will be paid some amount of money, which is a function of their report, their reported beliefs, and of the outcome. Okay, so S is, this contract is really a mapping from the set of distributions over outcomes. These are the agent reports and the realized outcome to like a dollar amount. Okay, so they're paid according to their report and the outcome. And this contract is known. So the agent will be deciding what to report based on what this contract is. And we'll call this a scoring rule. That's what S stands for. Okay, and then here's sort of the meat of the model, which sort of ties the thing that we want, reporting, the truthful reporting of the agent beliefs to the incentive model of the agent. What the agent is going to do is they are going to choose the report that maximizes their expected payoff, where the expectation is taken according to their own beliefs, right? Like we're not assuming that their beliefs are correct or even that it is a philosophically coherent thing to make probabilistic statements about what might be a deterministic world for all we know. We're only purporting that the agent has beliefs, which can be expressed as probabilities, and that when the agent figures out what they should report, they look at their expected reward, their expected payment according to this contract, given the belief they report, that's what they're optimizing over, in expectation when the outcome is sampled from what they believe to be the distribution over outcomes. Okay, so the model for what the agent is going to do is they are going to consider each of the reports they could make by thinking about what is the expected reward they are going to get from this contract in expectation over their own beliefs. And then they're going to optimize over that and report whatever set of beliefs, theirs or not, which maximizes their expected reward. Does that make sense? Yeah.
Instead of like trying to incentivize them to report P, create a function such that even if they report something else, there's only one valuation they could have really had to report P. I mean, I guess it's effectively like the same thing.
You could, I guess more generally, you could have asked this question much earlier in the mechanism design portion of this class and said, like, why are we like implementing things so that truth telling is a dominant strategy? Couldn't you have implemented things so that the dominant strategy was something else, but that we could figure out what your value was from what you're reporting by like inverting your best response function or something? And like you could, but in general, it doesn't help to. There's this sort of general notion called the revelation principle, which sort of says, look, suppose I had some crazy mechanism which implemented, say, in dominant strategies, something else. I am going to now describe to you like a mechanism that provides the same outcomes but implements in truth telling that something else. Here's the mechanism. I'll ask you what your value is, and then I will play I will play for you whatever was your dominant strategy in the more complicated mechanism I designed, given what your value was. And now it's a dominant strategy for you to tell me the truth. So a similar thing could happen here. Like if we had some scoring rule that somehow made it a dominant strategy for you to report, you know, some invertible mapping of your beliefs so that we could recover your true beliefs from it, we could generically convert it into a similar scoring rule that incentivizes you to tell us your beliefs themselves. So it's a good thought, but it turns out that kind of thing doesn't help. Good. Other questions? Okay. So our agent is going to be thinking a lot about like, what is their expected payment for reporting P if the outcome is drawn according to Q. And so first I want to give some shorthand notation for that because we're going to be talking about it a lot. Okay, so remember the contract as described takes as input two things, a distribution, that's the reported beliefs, and then an outcome. Like we see at the end who won the election. We don't see the probability with which they win the election. So now let me define this shorthand function that takes as input two distributions, P and Q. What does it mean? SPQ is the expected payment we will make to the agent if they report the beliefs P, but the state, the thing that we're betting on, is actually drawn from distribution Q. So this is going to be their expected payment if they believe the outcome is drawn according to Q, but they report P. Right, so this is just the thing they're maximizing. It's the expectation when the outcome is drawn according to beliefs Q of the payoff of the scoring rule of this contract when beliefs were reported to be P. And just expanding this out, this is just the sum over all of the possible outcomes, all of the possible realizations of the true probability of that outcome under belief Q times the payment that will be made given that beliefs P were reported and that outcome was realized. Okay, so it's an expectation. One thing to note is that this is a linear function of Q, because how does it rely on Q? It's just an expectation over Q, and expectations are linear. Okay, right, so this contract S, it could be complicated. Who knows, like, how it depends on P and Y, but the expected payment when the belief is P and the true distribution, or sorry, when the report is P, but the true distribution is Q, is linear in Q. Yeah? Okay. And so now we can define like our main object of study, which are called proper scoring rules, which are exactly those contracts that make it, under any beliefs the agent might have, a dominant strategy to truthfully report their beliefs. Okay? So how do we write that in our notation? Well, okay, a scoring rule, which again, remember, is an object mapping reports distributions over outcomes across actual outcomes to money, to dollars, is proper if no matter what your belief is Q, truthful reporting is a dominant strategy. Okay. So what that means is that S, for every Q, for every belief you might have Q, and for every misreport P that you might consider, SQQ, this is what you believe you will be paid in expectation if you truthfully report your beliefs, right? Where here the forecast is equal to the belief, is only higher than SPQ, what you believe you will be paid according to your true beliefs if you report something else. Okay, and if, right, so this is saying it should be no matter what your beliefs are, under your beliefs, it should be a dominant strategy to tell the truth. Okay, and if it is a strictly dominant strategy, if this inequality is strict whenever you report anything other than your true beliefs, then we'll call this a strictly proper scoring rule. Does this make sense? Like, and I think it's pretty intuitive. You know, like just as before, in writing down a contract and entering into a contract with this agent, we are inducing a game. In this case, a pretty simple game, like a one-player game. And we would like, the set of strategies in this game, here it's continuously large. It's the set of probability distributions over outcomes that they can report. We would like that in this game, it should be a dominant strategy for them to tell the truth, to tell us their true beliefs. And the whole point is we don't know what their true beliefs are. So this should be true no matter what their true beliefs are. Okay, they should make more money as evaluated under their true beliefs if they tell the truth than if they do anything else. As a result, if they're trying to maximize their payment, they should tell us their beliefs. Okay, this is the property that, like, our attempt at paying people in sort of proportion to the probability they told us on the actual outcome failed to satisfy. There was something they could do that would make them more money than telling us their true beliefs. And even worse, it wasn't invertible, so we couldn't figure out what their true beliefs were from that. Okay, so so we've now laid out the model and sort of the thing we want, and so does all make sense. The model in which we are working, sort of this object we want, which is basically just a contract that makes it that makes truth-telling a dominant strategy. Right, so your type here is sort of your beliefs. The only possible, like, subtlety here is that, you know, like, we're not assuming some true underlying distribution. When we're taking expectations for the agent, it's always under their own beliefs. Everyone on board? Okay. So let's now take a brief aside and just sort of remember convexity. You know, okay, yeah, like when I was in elementary school, right, like the question was like, you know, what's convex and what's concave? Like one of them is like this, one of them is like this. And what I was told and has stuck with me is that the way you remember this is that concave is the one that looks like a cave. Okay, so that one's concave. So what is a convex set? So a convex set, we'll get to this one in a second, by the way. A convex set, you know, there's a convex set, there's convex sets, and there's convex functions. So a convex set is any set of points such that if I take 2 points within the set and draw a line between them, every point on the line is also contained within the set. Okay, so a circle is a convex set. If I had some wonky shape that looked like this would not be a convex set because, for example, if I took these 2 points and drew the line between them, I would have to step outside of the set. So convex sets are sets that contain the line connecting any 2 points within the set. Okay, written in notation, you know, these are two-dimensional pictures. In d dimensions, once again, a set is convex if it contains the line segment connecting any 2 points. So in other words, for any pair of points x and y in the set, and for any weighting between 0 and 1, if I take the convex combination of these 2 points according to this weighting, just the linear interpolation of them, that also lies within the set. Okay, so that's what convexity is for sets. Now I can also talk about concave functions. Those are the ones that are not, that do not look like caves. Okay, so things like this. What's a convex function? Well, a convex function, if you like, consider the set of points that lie above the function. Okay, like the stuff that's above the curve. This is some set of points. The function is convex if the set of points that lies above it is convex. Okay, so equivalently, right, if I take any 2 points on the curve, the function defines, and then take the linear interpolation between them, all of the points on this line have to lie above the function because the set of points above the function must be convex. So in notation, again, for any pair of points x and y, and for any weighting that I could use to interpolate between them, if I evaluate the function on the corresponding interpolation between the 2 points, that always has to be smaller than what I get from the linear interpolation of the function values. Okay, that's the definition of convexity of a function. Yes.
This probably isn't important, but I'm just curious, are convex and concave sets complements, or are there some sets that are like that?
Yeah, I guess I don't really know what a concave set is. Yeah, like I think concave functions are just -1, times convex functions, the negative of convex functions. Okay, so far so good. So there's another way to define convexity, or it's a characterization of convexity that you can prove, although I will just assert it, which is that if you look at a function like this, and then you take any point on the function and you draw its tangent line, or like its gradient, then what you'll always find is that that line lies below the function. Right? I can do that at any point. If I draw the tangent line, it lies below the function if the function is convex. Okay? So here's a fact, which is, like a theorem. You could either define convex functions this way, or you could prove that convex functions, as we've defined them, satisfy this property with a little bit of calculus. Here's the property. Suppose I've got some function, d-dimensional function, and then let's say it's differentiable, just so it makes sense to talk about the gradients of this function, although that's not actually strictly necessary. Then it's convex, it turns out, if and only if, for every pair of points x and y, if I look at some point y, and then I look at sort of the line that is tangent to the curve at that point. So I look at f of y plus its sort of linear extension that I get by just taking the gradient of the function, which in one dimension is just the slope of the tangent line. Right, and look at the line with that slope, with that gradient. That this line always lies below the function value. Okay, so that's just this in pictures, that if I take the tangent line at any point on this function, the tangent line always lies below the curve. Okay, or equivalently, for any x and y, it's always the case that f of x is only bigger than f of y plus the dot product of the gradient with y and x minus y. This is just sort of a linear function that is tangent to f at y. Yeah, like this is just the linear function that's tangent to f at y. Okay. Does that make sense? Like, if you're not comfortable with like gradients and stuff, like I think it's really a pretty simple idea from pictures, right? Like if you draw the tangent line, if the function's convex, it lies below the function. Yeah. Yeah, so like suppose you had like a convex function that was not differentiable, then you could define something called a subgradient. Basically, a subgradient would, like anything that, all of these are subgradients, basically. But all of the subgradients are underneath it. but we won't talk about that. Okay, but like, yeah, if you've got like the absolute value function, it's not like you can't talk about this stuff. Okay. Does that make sense? Okay. So let's try to build some intuition, maybe by going back to the binary prediction case. Okay. So the nice thing about the binary prediction case is that beliefs are one-dimensional, right? Like your distribution over the outcomes can sort of be summarized by like a single number, P. What is the probability you think A is going to win the election? Because your belief for the other outcome has to be 1 minus P. Okay. So, all right. So remember, like we have this expression for if your beliefs are Q, if you think there's really a Q probability that A will win the election, but you report belief P, what is your expected payoff? Well, if A wins, which you think happens with probability Q, you get SPA, what the contract tells you you get when A wins the election. If B wins, which you think happens with probability 1 minus Q, you get SPB. Okay, and remember, this is linear in Q. And let's say that f of Q is SQQ. That is, f of Q represents if for someone whose belief is Q, how much money they get in expectation by telling the truth. Okay, right? Like S in general has two arguments, what you report and what you believe, but if you tell the truth, they're the same thing. And then F of Q is how much someone who tells the truth expects to get as a function of their beliefs. Okay, so let's make a couple of observations. The first observation, as we already noted a few times, is that the amount of money you expect to get is linear in Q. It's linear in your beliefs. Okay, so like, for example, let's say that the x-axis here is Q, and we are plotting the amount of money that you expect to get if you report a 20% chance that A wins the election. Well, like I don't know what the slope of that is. It'll depend on various things, but like it's a linear function. Okay, so it'll look like this. Okay. Now, if S is proper, if it's always a dominant strategy for you to tell the truth, then no matter what your belief is, reporting your true belief, F of Q, always makes you more money than reporting any other belief. Okay. And yeah, and so as a result, what that means is that F of Q, the amount of money that you make by truthfully reporting, if you have belief Q, is the maximum over all P of S of PQ. Right? This is the maximization problem you're solving when deciding what to report. You're gonna pick the report that makes you the most money. This is the expression that tells you how much money you think you're gonna make if your beliefs are Q and you report P. Truth-telling, the properness property, means that F of Q can only be bigger than all of these, right? There's no misreport that causes you to be able to make more money than telling the truth. And definitionally, f of q is equal to s of q. It's, you know, we get equality when p equals q. So so f of q can't be bigger than the max, right? So f of q is equal to the max of all of these functions of q. Now these are all linear functions. So that means that f, you know, there's, you know, for different values of p, s of pq will be a different linear function, right? So for different values of p, there will be different linear functions. Okay, you know, there'll be continuously many of these, but f, whatever it is just the maximum of all of these linear functions. Okay. So first of all, like the maximum of a bunch of linear functions is convex. Okay, you can sort of see that in pictures. I guess you could probably, with some work, draw a neater picture than that, but you could sort of convince yourself by drawing pictures, drawing a bunch of linear functions and taking the max, that the maximum of a bunch of linear functions is convex. But maybe sort of a more algebraic way of sort of verifying it is that s of pq, this linear function, is the tangent line of f of q at p equals q. Why? Well, it's linear and it's equal to s of q by definition. It's equal to f of q at p equals q. And by properness, it lies entirely below f of q, right? That's the properness condition, that f of q is only above s of pq. Yeah. It's a tangent line. Yeah. If f is differentiable, it will be the tangent line, but it is a tangent line. But I guess, but the point is, all of the tangent lines by properness are going to lie below f, which is why f is convex. Or you can just try drawing a bunch of linear functions and convincing yourself that the maximum of a bunch of linear functions is convex.
Yeah, I'm just like looking at that picture. Oh, there's points where there's no.
Yeah, but that's because I only drew that finitely many lines, so it's piecewise linear. But yeah. Okay. Okay. Okay, so here's the theorem. We're gonna sort of completely characterize the set of proper scoring rules. Okay, and it's going to be sort of very closely related to the set of convex functions. So fix any setting of the sort that we've discussed. So any finite domain, let's say the cardinality of the domain is D. A scoring rule, again, a mapping from beliefs across outcomes to dollar amounts, is proper if and only if we can express the, if and only if we can express the expected payment that you're going to make as a function of your report and your beliefs in the following way, as a function of some convex function f. Okay, so it's proper if and only if there exists a convex function, a d-dimensional convex function, so that the agent's expected reward when they believe q but report p can be written as f of p plus the gradient of f of p dot producted with q minus p. Okay, like in particular, right, this means that if I want to know how much I need to pay you given a particular reported belief p and a realized outcome y, that the payment rule is, you know, f of p plus the dot product of the gradient of f of p with what is this? This is the standard basis vector that puts a 1 in the coordinate corresponding to the realized outcome, and a 0 everywhere else, minus p. Or equivalently, just the special case of this expression for the distribution that corresponds to outcome y happening with probability 1. Okay. So what this theorem is giving us is basically a generic way, number one, to generate proper scoring rules. There's many proper scoring rules, and if I want to come up with a proper scoring rule, I can just come up with my favorite convex function and write down, this contract. This is my proper scoring rule. And on the other hand, a way to verify that scoring rules are proper. If I can write my scoring rule in this form with respect to some convex function f, it is proper, and that is the only way it can be proper. Okay, this is a if and only if characterization. Okay, and then finally, just sort of like an observation, this convex function will always be just the amount of money that the agent gets in expectation if they have beliefs Q and truthfully report. Okay, I mean, that you can just read off of here. If P equals Q, this last term empties out, right? And so if they truthfully report Q, they get F of Q dollars. Yeah.
Does the function need to be convex from like all of RD or like the entire domain, or
it only needs to be convex on the reporting domain, so on the domain of probability distributions. But let's just say it's convex everywhere to avoid some notational hassle. But yeah, like, this function, its domain isn't really, the domain is not really sort of all of R to the D, it's just probability distributions over Y, and it's enough that it's convex over that domain. Okay, questions? So this is sort of like a characterization theorem. It's saying, like, like proper scoring rules all have this common form. There's many of them, of course, because there's many convex functions, and you can try to look for your favorite one that satisfies, there's other properties you might want that you can try to optimize for subject to properness. Again, think of properness as like an incentive compatibility constraint. But if you are going to do that, essentially your optimization problem is going to boil down to just optimizing over convex functions f. All proper scoring rules are specified by, are characterized by some convex function f. Does the theorem make sense? Okay. So there's two directions to prove, because it's an if and only if characterization. So in the first direction, I want to say, look, like we'll go in the direction first of generating the proper scoring rule. You give me a convex function, I will produce a scoring rule for you, and we will verify that it is proper. Okay, so we need to show that if f is convex, then the scoring rule that is defined as in the theorem, the payment that is made when you report beliefs P and the outcome Y is realized, is f of P plus the inner product of the gradient of f of P with the Y standard basis vector minus P is proper. And so we can start by just sort of like doing some computations. So like, first of all, what is the expected payment for, what is the expected payment you get when you make report P and yet you believe the outcomes are drawn from Q? Well, it's the expectation over outcomes drawn from Q of this expression. But most of these terms are independent of the randomness in the expectation. Most of these terms do not depend on Y. The only term that depends on Y is here. And so we can pull the expectation through to the very inside and just sort of get that the expected payment is of the expected form. It's f of P plus the gradient of f of P dot producted with Q minus P. Question? Okay, so this is the payment in general if you report truthfully. Sorry, if you report non-truthfully, if you report P, not necessarily Q. On the other hand, like if you do report truthfully, then what is your expected payment? Well, if you report truthfully, your expected payment is SQQ. Well, if Q equals P, this term zeroes out, and so your expected payment is just F of Q. And so what is the condition that the scoring rule is proper? What is the condition that you're better off reporting truthfully than lying? Well, it's just the condition that the expected amount of money you make if you report truthfully, which we just observed was F of Q, has to be bigger than the expected amount of money you make if you lie, which is this expression. But this is one of our definitions of convexity, right? This is saying at any point Q, F of Q has to be above its tangent line, right? This was our sort of like our second characterization of convexity. It's exactly this. If F is convex, it satisfies this property, which, because of how we've written down the scoring rule, is exactly the truthfulness condition. Yeah.
The scoring rule has Q within it. It's like how do you use the? I think I'm misunderstanding something. How do you use like first trying to elicit information? You know what Q is when you're.
So the scoring rule is defined as follows. It does not make reference to Q.
Oh, okay, that's just the expectation.
But this is sort of important, right? Like in this whole model, like how are we, like, what is the connection to ground truth? How are we like getting people to elicit their true beliefs, given that we are not assuming that their true beliefs are necessarily correct? And so the only external thing we observe, which is the realized outcome, it's not necessarily sampled from their true beliefs. So how could we possibly get them to tell us their true beliefs? Well, it's because we're assuming that the thing they are maximizing is their expected utility under their own beliefs. And so when you take this scoring rule, which doesn't make any reference to Q, but then you compute the agent's expected revenue under their own beliefs, then you get an expression which does contain a Q. That's what's going on. Does that make sense? Okay, good. Okay, so that was the one direction. If we have a convex function, we can always turn it into a proper scoring rule. We also want to argue that that's the only way, that all proper scoring rules have this form. So in the reverse direction, what we need to show is that if you give me a proper scoring rule, then there is a convex function such that I can write the proper scoring rule, which initially didn't take this form, perhaps in this form, right? I need to exhibit a convex function f so that I can express your proper scoring rule as f of p plus the gradient of f of p, inner product with the y standard basis vector minus p. Okay, so what function f are we going to choose? Well, the function f we're going to choose is the same one from the other part of the proof. It's going to be, f of q will be defined to be the expected revenue under belief q of truthful reporting. Okay. Okay. So remember, we have this expression for the expected revenue that our agent will get if they report beliefs P, but they truly have beliefs Q. Okay, this is a linear function of Q. And because we've been promised that the scoring rule is proper, we know, so just a couple of things to note about it. we've got this function f of q. This is a linear function of q. It is tangent to f of q because, by definition, when p equals q, it's equal to f of q. F of q is just sqq. And properness tells us that this tangent line always lies below f. How come? Well, like f of q is the expected profit you would get for truthfully reporting if you had beliefs q. S of pq, this is the expected profit you'd get for misreporting p if you had beliefs q. And properness says it's always better to truthfully report. Right? So properness tells us that this linear function, which is tangent to f at q, must lie below f of q. Okay, and so, like for any p and q, one way we can write s of pq is as follows. It's a linear function, and we know the value of the function at one point, right? So like think about this in 2 dimensions, maybe. Like we've got our intercept. When q equals p, we know it's equal to f of p. And then we've got our slope. That's the gradient of f of p. Okay, and so this is the expression for a linear function tangent to f at point p. And properness tells us that all of these linear functions lie below f, which means that f must be convex. Okay, so that's the other direction. And so I want to now just sort of go through one example and then maybe wave my hands at some relationship to machine learning. Okay, so like there's many proper loss functions, right? There's one for every convex function. But let's maybe just sort of think of a few, or one for now. So I claim that the loss function. Okay, so what did we like try to do at the beginning of the lecture? We were like, all right, let's try the scoring rule that in the event that outcome y is realized, pays you the probability that you reported for outcome y. That didn't work. Here's a different one. This scoring rule says, in the event that outcome y is realized, what I'm going to pay you is in proportion to the log of the probability you reported for outcome y. Okay? I claim this one is proper. This one does incentivize you to tell the truth. So let's write out the expected payment you would get if you report distribution P, but Y is actually sampled from distribution Q. Okay. Well, that expected payment is equal to this expression, the sum over all of the outcomes of the probability of the outcome under Q of times log of the probability of the outcome under P, which if you've spent time training neural networks, you might know under the name of cross entropy. Okay, this would be, or negative of cross entropy. This would be sort of a common thing to maximize as a machine learning objective. Is it proper? Well, let's check our characterization. F of Q here, the expected revenue you get if your beliefs are Q, if the outcome is drawn from Q and you report truthfully. In this case, is this expression here, which you might recognize as the negative Shannon entropy. But one thing that's relevant about the Shannon entropy is that it's convex. Okay, so f of q is indeed a convex function. And we can go through the exercise of trying to write down our scoring rule in terms of our characterization and see if we recover our original scoring rule. Right? So like we're going to have to think about the gradient of f of q. Well, what's the derivative of f of q with respect to outcome y? Well, the derivative of log x is 1 over x. Okay, so like I guess the product rule tells us that the derivative of this term is going to be, log of q of y plus 1. Okay, so we write out our characterization here, right? It's f of p plus the gradient of f of p times the y standard basis vector minus p. F of p, we know what it is. It's the negative Shannon entropy. The gradient of f of p, the y-th coordinate of the gradient of f of p, it's just 1 plus log of p of y. Okay, and similarly here, and all of the terms cancel, and what we're left with is log of p of y. Okay, which is to say, we have verified the characterization that log of p of y, which I asserted was a proper scoring rule, actually can be expressed in the form that our characterization claimed that all proper scoring rules could be expressed. And therefore, this is indeed a proper scoring rule. Okay. So cross entropy, a common objective in machine learning, that's a proper scoring rule. Like in linear regression, say, if you take a sort of introductory statistics course and you learn about linear regression, where you're minimizing squared error. Squared loss, where I pay you in proportion to the square of the probability that is realized, that's also proper. Right, so you might have wondered at some point, like, why is linear regression, say, defined as minimizing squared error? Why not absolute error or something else? Why, when we're solving regression problems with neural networks, do we minimize cross entropy or sometimes squared error and not something else? It's not a coincidence. Like, if what you are trying to do is solve a regression problem that will recover for some label you are trying to predict, the probability distribution on that label, conditional on the features, then you'd really like that your loss function should be proper. Why? Well, if it is, then the unconstrained optimum to the optimization problem that says maximize the score or minimize the negative of the score, minimize the loss, where the labels come from training data that is drawn from some distribution. This is like the outcome that is realized according to some distribution. This minimization problem will be minimized at the true conditional label distribution if your loss is proper. Because just as your gambling policy wonk friend is trying to maximize his payment, like when you unleash gradient descent to try to minimize some loss function, like the only thing it's going after is monomaniacally minimizing the loss function. And so what you'd like is that the loss function should be minimized at the real probabilities, not at something else. That is not true of all loss functions. It's, for example, not true of absolute loss, as we saw at the beginning, but it is true for proper loss functions. Okay, and so this is an important reason why, for example, standard regression problems minimize squared error rather than some other measure of error. It's an important reason why you see cross entropy showing up as an objective in multi-class classification. It's because these loss functions are proper, and so the minimization problem which you are solving is pushing you towards the true conditional label distribution, not something else. Yeah.
Absolute loss just
So it is, well, it's not clear that it would have worked, but it is true that in our definition of properness and throughout the lecture, we have assumed that the agent is just an expectation maximizer. So if your agent is not an expectation maximizer, if they care about things like the variance of their payment, then proper losses are not necessarily going to elicit the truth. But that just means things are more complicated. You're going to have to try to design contracts specifically tailored to their risk aversion, not that like absolute loss is going to somehow elicit the truth. Other questions? All right, and I'll see you guys on Thursday.